Welcome, students. So glad you're here for today's explainer on the C04 module of the 42 Piscine. Think of me as your personal professor for the next few minutes. We're going to break down these exercises step by step so you can confidently conquer both the automated grading of the Moulinette and, of course, those strict formatting rules of the Norminette. If you've been kind of struggling with pointers, strings, or number conversions, hey, take a deep breath. We've got this. We're going to build this up logically, starting from the absolute simplest string functions all the way up to some pretty complex custom base conversions. So grab your notebooks, get comfortable, and let's get to work. Okay, here's our game plan for today. We'll start with strings, length, and output, then move into integers and the overflow trap. After that, string to integer conversion, followed by custom number-based systems, and finally, we'll wrap up with final submission and Norminette.
All right, section 1, strings, length, and output. Let's dive right in.
Let's lay the groundwork with exercises 00 and 01. These are literally your foundational building blocks. I promise you, if you understand these perfectly, the rest of the module becomes infinitely easier. So for your very first task, exercise 00, FT stringlen, your core objective is simply to iterate through a character sequence until you hit a very specific byte. You see, in C, strings aren't inherently aware of their own length. They're really just contiguous sequences of characters in memory. So what actually tells the computer to stop reading? Well, it's the null character, represented as \0. This tiny byte dictates the absolute termination of your string. Finding this, that's the entire secret to string manipulation in C. Here's your logical roadmap for exercise 00. My biggest tip for you here, keep it incredibly simple. First, just set your counter variable, an integer, to 0. Second, set up a basic while loop that checks if your string at index I is not equal to that null character. Third, safely increment your counter right inside that loop. And fourth, return the total value. Seriously, do not overcomplicate this with fancy pointer arithmetic if you aren't comfortable yet. A simple array index works beautifully and it'll pass the test every time. Moving on to exercise 01, ft_puts_str. Here you need to print that string to the screen, and you face a bit of an architectural choice. Option 1 is to iterate character by character, calling the right function inside a loop. Now, this works, sure, but it's computationally heavy. Instead, here is a massive pro tip from me to you. Reuse your brand new ft_strand logic. Just find the total length of the string first, and then issue a single write command for the entire block. It's highly efficient, it's elegant, and it shows the graders you have a deep understanding of how system calls actually work. Moving right along to section 2, integers and the overflow trap. Let's look at exercise 02 and see how this builds into our next major challenge, converting and printing integer data types. Now, printing a string is relatively easy, right? Because it's already characters. But printing a number requires converting numerical values into ASCII characters so the screen can actually display them. Before you just jump into your IDE and write a recursive function to print numeric digits, I want you to pause for a second. As your professor, I need you to consider a critical edge case that traps countless students and completely ruins their Moulinette score. What happens if you take the absolute lowest negative 32-bit integer and multiply it by -1 to make it positive? Any guesses? Well, the absolute lowest number is exactly this, -2147483,648. And here is the trap. Standard signed 32-bit integers cap out at a positive maximum of 2147483,647. Did you catch that? Notice that the positive limit ends in a 7, but our negative limit ends in an 8. Meaning, if you blindly flip the sign on this absolute minimum value, your code is going to mathematically overflow. It literally cannot fit into a standard integer. The behavior becomes completely undefined, your program breaks, and yep, you fail the exercise. So the absolutely crucial point here is how you bypass this trap. My advice? Trap this exact minimum limit independently. Just use a specific if condition right at the start of your function. If the number matches this exact negative value, just use your write function to print out -2, and then pass the rest of the number, the 147, 48, 3648, into your normal recursive logic. Or honestly, even simpler, just explicitly print the whole string, -2147,483,648, and return. Handle the edge case manually so you don't let the automated grading systems catch you off guard. Okay, section 3, string to integer conversion. Let's keep this momentum going. Now that we understand how numbers are broken down into characters, let's reverse the whole process for exercise 03 with ft_atoi. This function takes a string of characters and converts it back into a usable integer format. Think of your logic for this exercise in 3 sequential, distinct phases.
Please don't try to do everything at once. Phase 1. Bypass all those invisible white space characters, spaces, tabs, new lines. You can just check for ASCII values 9 through 13 plus 32. Phase 2. Calculate the final mathematical polarity. The rule of thumb here is that an odd number of minus signs means the final number is negative. So just loop through and multiply a sign variable by -1 every single time you see a minus. Phase 3. Once you finally hit numbers, start parsing the numeric sequence. And remember, the very moment you see a non-digit, you stop entirely. To safely accumulate those ASCII characters back into true integers, you're going to need a very specific mathematical formula inside your loop. Let's break this formula down together. You take your running result, multiply it by 10 to shift the digits left, and then you add your current character. But, and this is a big but, you can't just add the character 5 directly, because in ASCII, the character 5 is actually the underlying value 53. So, by subtracting the character 0, which happens to be ASCII 48, you get the true mathematical value of 5. Apply this simple formula in your loop, multiply by your sign variable at the end, and boom, you have a perfect ft_ATOI function.
All right, Section 4, Custom Number-Based Systems. You're doing great. Stick with me.
Okay, let's take a collective breath here. We are officially entering the most challenging part of today's explainer. Exercises 04 and 05 really represent the final bosses of this module. ft_putNumber_base and ft_ATOI_base. We're basically taking everything we just learned about base 10 mathematics and applying it to custom number-based systems. I know it sounds a bit scary, but honestly, it's just swapping out a few variables. Now, for both of these advanced exercises, your very first step must be validation. The user is going to pass you a string of characters that represents the custom base. If that base string violates any of these strict validation rules, you must immediately return 0 or display absolutely nothing. For instance, the base length cannot be 0 or 1. I mean, a base 1 system just doesn't work here. It cannot contain duplicate characters, and it cannot contain a plus or a minus sign. My tip, write a dedicated helper function just to check these rules before you attempt to do any math.
For ft_number_base, here is your structural roadmap. First, validate the base using the exact rules we just discussed. Second, manage your negative signs and that exact same minimum integer overflow trap we talked about earlier. Don't forget that. Third, the real magic. Recursively split the number. But instead of dividing by 10 like you did back in ft_number, you divide by the length of the custom base string. Just treat the mathematical length of the custom base string exactly as you treated the number 10 in our earlier logic. It's the exact same concept, just a different scale. Now, moving on to our final exercise, ft_A2I base. Let's actually compare it to the standard ft_A2I. Standard A2I accumulates value using base 10 math and ASCII offsets, right? We literally just subtracted 0. Well, ft_A2I base simply marries the whitespace and sign parsing of regular A2I with this brand new positional indexing logic. Because your base characters could be literally anything, like say ponyvef for base 8, you can't just subtract 0 anymore. That won't work. You need to actually find what index position the current character occupies inside that custom base string. Remember our earlier formula? Well, we're updating it. We just swap out the number 10 for our new base length, and we swap that ASCII subtraction for a helper function that resolves the custom digits value. Let's visualize this. If your base string is ponyvif and you read the character n, your helper function searches the string, finds n at index 2, and returns 2. So your math simply becomes result equals result times 8 plus 2. Master this one formula, and you have officially mastered the hardest logic in the entire C04 module. How cool is that? Section 5. Final submission and Norminette. The finish line is in sight.
You've built all the logic perfectly. Your code is honestly brilliant. But wait, before you rush to submit your repository for grading, let's quickly review your final syllabus rules. The automated grader has absolutely no mercy. Do not let a silly, simple formatting error ruin hours of hard work. Systematically check that your code passes every single one of these strict Norminette constraints. Ask yourself, are your functions under 25 lines? Do you have more than 5 functions packed into a single .c file? Are all your variables declared right at the top of your function blocks before any logic happens? And finally, did you verify that only the required .c files are sitting in your turn-in directory? Please, no random .out files or text files left behind. Clean up your workspace.
Congratulations on conquering the core concepts of the C04 module.
But I want to leave you, my students, with this final thought and a bit of a challenge. Have you actively tried to break your own code? The true test of a programmer isn't just writing code that works perfectly for the happy path. It's knowing exactly how to test the absolute worst, weirdest edge cases imaginable. So go test those negative minimums. Test empty bases. Test strings with 50 minus signs in a row. Be ruthless with your own work. Thank you so much for joining this explainer. Go test your code, and the absolute best of luck with your submissions. You've got this.